So today we're going to start with the sensitivity analysis part, and then duality will take time, but we will get there as well. Well, what is sensitivity analysis? We have modeled a problem, we have solved the problem somehow, and now we are trying to determine if we can, change the problem without changing the solution, or what happens, does the solution change if we change a part of the problem? This is what we are looking for, and this is called sensitivity analysis. So how are parameters? How does one of our numbers, one of the numbers that we picked, for example, a coefficient of the, objective function or a right-hand side value, how does that parameter affect my model, my solution? In fact, we're gonna, try to understand how that, works, and this is called sensitivity analysis. So, for example, we were selling stuff. Okay, we were trying to maximize our profit, and we were selling stuff. For example, from the, Dakota furniture example, we had 60, 30, and 20, I think, as prices, and that 60 was a high price, 30 and 20 were lower, and the value of 60, which is the price of X1, was in the solution. We already knew that 60 was a good price, so X1 was going to be constructed, manufactured, and sold. So what about the others? Or what happened if we had, decreased X1, value of X1, which is 60, or increased it? What would happen? Can they change? Yes, they can. And there are lots of, different, solutions you can achieve by changing those numbers. You can take, for example, a non-basic variable and increase its value for a maximization problem, and then have it, become a basic variable at the end of that increment, or decrease the value of a basic variable and make it a non-basic variable. But still, you have to see how that change affects your model without solving your model from, scratch, from zero. You don't want to solve the model every time you are, thinking of making an analysis for just one or two parameters. So we need to see how this, happens, how we can do the sensitivity analysis without solving the model every single time. This is the most important part. We don't want to solve it every single time. We just want to see how the changes can happen, okay, without the added extra work, which is something everyone wants to, get out of. So we need to know two things. We have to learn two things to be able to talk about sensitivity analysis clearly. The first one is the reduced cost, and the second one is the shadow price. Now, reduced cost is the, let's say, value of a non-basic variable, objective function value, that it can increase, the amount of increase that it can have before it enters the solution. Which means that, for example, we have a basic variable. Let's just write something. Let's just say that this is 10x1 plus 20x2. We are trying to maximize something like this, for example. And we know that at the end of the solution becomes x1 is equal to 0 and x2 is equal to, let's say, 15. Now, this is my solution. But as I can see, x1 is a non-basic variable and x2 is a basic variable, because x1 is a value of 0 and it's most probably a non-basic variable. It could be a basic variable with a value of 0, but we just assume, let's just assume that it's a non-basic variable, and x2 is a basic variable because it's inside the solution. It's in the solution. So the reduced cost is applicable for x1 only. X2 is already a basic variable, so its reduced cost is 0, because reduced cost is the amount you have to increase or decrease depending on the model, max or min. In max, it's increase. In min, it's decrease. It's the amount you have to increase your objective function coefficient, which is 10 for x1 over here. How, for example, if you increase this 10 to 25, then x1 becomes viable, okay? If 25 is your limit to make x1 viable, to make x1 a part of the solution, then your reduced cost is 15, because you have to increase 10 to 25. The difference is 15. Or if it's 17, if at 17 x1 becomes viable, becomes part of the solution, then your reduced cost is 7, okay? This difference, this minimum difference that you can have to get x1, that non-basic variable, into your solution as a basic variable. This is your reduced cost, okay? How much increase do I need in here? And then there's a shadow price. Now, shadow price is for the right-hand side. So, for example, let's say we had 2x1 plus 3x2 is less than, you can write it, why can't I? Yes, over here, 45. For example, we had a constant like this one for this question as well. So x2 equals 15 holds at least. x1 plus 2x, 3x2 is equal to 45. Now, in here, we now know that this 45 is our right-hand side, okay? And the shadow price is the amount of, let's say, increment you can find or amount of increase you can get from your objective function if you increase your right-hand side by 1 point. Now, this is for maximization, of course. The improved part is for maximization. The increased part is for maximization. So if I increase 45 to 46, how much will my Z value change? At the moment, my Z value is 15 times 20, which is 300. That's okay. But if I had this one 46 instead of 45, how much of an increase would I have on my Z value? This is my shadow price, okay? How much is the Z value improved? So if I increase my right-hand side by 1 point, how much does my Z value increase or improve? It can be a positive value, it can be a negative value as well. Negative improvement, which means that you're actually getting something, getting a negative effect from your increase on the right-hand side, which is possible, by the way, because there are other signs as well. You don't have to write less than or equal. It might be greater than or equal for a maximization, which might cause some, discomfort and reduction in your Z value as well. That can happen. Still, if I'm increasing the right-hand side by 1 point, how much of an improvement will I get from my Z value? This is the shadow price, okay? Reduced cost is for non-basic variables in your, objective function. It's about the coefficients in the objective function. The shadow price is for right-hand sides, okay? Reduced cost is about the amount of increase you can give to a objective function coefficient of a non-basic variable. Shadow price is about the improvement you can get by increasing your right-hand side by 1 point. Okay, these two are important concepts, the most important concepts in here at least. Now, assuming we know these two, I know that it's not that clear right now, it's a bit hazy, but it's always hazy at the start, so it will get better as we solve examples. Now, we have a simple example over here. 6 times x1 plus x2 plus 10 times x3, subject to x1 plus x3 is less than 100 and x2 is less than 1. And this is a maximization, and we have three basic variables, three variables here, and we know that we have two coefficients, so at most two of them can be basic variables and one of them should be non-basic. So two can be in the solution, one has to be, at least one has to be on the outside, and by looking at here only, just looking at these constants, I can solve this without using simplex or anything because it's a simple model. Now, as you can see, x1 plus x3 is less than 100, so I have to pick one of them, okay? x2 is less than 1. Okay, x2 is independent from x1 and x3, so I can just pick x2 as 1, which will give me a value of 1 over here. And between x1 and x3, I have to check which one gives me more value, which is x1 is giving us 6 and x3 is giving us 10, so x3 is giving us more value. So x3 is equal to 100 and x1 is equal to 0 is a solution for me, which is also the optimal solution over here. So I will get 10 times 100 plus 1, 1001. So my Z value is 1001, my x1 is 0, my x2 is 1, and my x3 is 100. So these are my values. Okay, this is easy to calculate. We can also use simplex to find the solution in 2 iterations, I would say, but still we can just find it by hand as well. And then we have to make the sensitivity analysis. So I have one non-basic variable, which is x1. So reduced cost will only be implemented for x1. The others, x2 and x3, have a reduced cost of 0. I already know that because they are basic variables. So I have to check the reduced cost of x1. So x1, how can I enter x1 into the solution? I have to check, okay, how x1 can enter the solution. How much of a raise do I need to get x1 into the solution? Simple. x3 had a coefficient of 10, and they have the same coefficient in the constraint, so they don't consume differently. So they consume the same amount of raw materials if this is raw materials, which is 100. So I can just say that as long as x1 gives me the same profit, x1 can enter the solution. So all I have to do is just raise the value of 6 into 10, which means that if I can get this 6 increased by 4, I can get 10, which means that my reduced cost for x1 is 4. So I have already said that x2 and x3 are basic variables, so they have a reduced cost of 0, and x1 has a reduced cost of 4. Because all I have to do is just get this x1 to its coefficient up to 10. So it would give me the same amount of profit as x3 giving, and they have the same coefficients in the constraint, so there is no priority, there is no consumption difference. It's simple as that. Any value above 10, x1 will be in the solution for sure, and x3 will be aborted. It will not be produced anymore. If this is 10, you have an alternative solution. You can find any value between those, x1 and x3, as long as they have a value of, the total has a value of less than 100. So it can be 50 to 50, 40, 45 to 55, 1 to 99, whatever, or 0.5 to 99.5, vice versa. It can change and it can be anything. If this is 10 as well, but if this is 11, then x1 will have all the 100 resources and x3 will not have any resources at all. So the constraint will work for x1. But if they're equal, they can just share. Now, this is the reduced cost part. What about the shadow price? For shadow price, I have to check what can change if I increase these values by 1. Now, for the first constraint, okay, the shadow price of the first constraint, if I increase this 100 to 101, then x3 will increase 1 point as well, because x3 has a value of 100 right now. If I get this to 101, then x3 will become 101 as well. So this increase of 1 point in x3 will result in an increase of 10 points in z value. So the right-hand side increase in the first constraint will result in 10 points of an extra profit for the model, for the objective function. So the shadow price for the first constraint is 10. For the second one, if I increase this 1 up to 2, then x2 will increase by 1 as well, which will result in an increase of 1 point for the z value, for the objective function value, which means that there's actually a shadow price of 1 for the second constraint. Okay, any questions up until now? These are the simple versions of them, the reduced cost and the shadow price. Any questions up until now? Can you understand what I'm talking about right now? Any confusion in here?
Hocam x1'i almamamızdaki sebep x3'ün katsayısının daha büyük olması mıydı?
Aynen öyle. Şöyle düşünebilirsiniz burayı. x1 ve x3'ün birer tane katsayısı olsaydı eğer, mesela bu 2x1 burada 3x3 olsaydı, o zaman oranlamanız gerekirdi. Düz bir oran yapmanız gerekirdi. 6 bölü 2, 10 bölü 3. Hangisi daha büyük değer veriyorsa o çözüme girer diye düşünebilirdiniz. Bu çok basit tabii ki. Hani hepsi birbirinden bağımsız bir şey olduğu için, x2 diğerlerini etkilemediği için, çok basit model olduğu için böyle yapabiliyoruz. Normalde yapamayız tabii ki, simplex yapacağız ama hani burada öyle bir şey olsaydı mesela 6 bölü 2'ye 10 bölü 3 olacaktı. 3.33'ten yine x3 kazanacaktı. x3 çözüme girecekti tam değer olarak da. Ama 3x3 olduğu için alacağı değer 33.3 olacaktı mesela 100 bölü 3'ten dolayı gibi.
Anladım hocam.
Burada x1'in değeri x3'ü yakaladığı zaman sadece şey olabilir. Hani x1 çözüme girebilir. O yüzden şu 6'nın hani yükselmesi gerekiyor. Burada da oran 6'ya 1, 10'a 1 aynı olduğu için, yani 6 ve 10 olduğu için oran, bu oranı yakalamak için bu 6'nın 10'a çıkması gerekiyor şu anda. 6 10'a çıktığı zaman aynı parayı kazandırabilir hale geliyor. x3 yerine x1'i alarak aynı parayı kazanabiliyorsunuz demek oluyor. Okay, then now we will talk about other, let's say, stuff as well. We will start with the graphical sensitivity done by analytical rule, then Lindo. Lindo will be the last part. I have already added graphical sensitivity and 100 rule to your Ninova screen, so you can just download from there. And let me just open up the graphical analysis. Yes. Now, this is something we already know, the Geppetto model. We have already solved this. We have seen how the solution works. We have seen how the graphical solution works in here as well. We know those constraints, so this is something we are familiar with. And this is from the book of Winston, by the way. So we know the solution already. We know that x1 is equal to 20 and x2 is equal to 60 and the z value is 180. Up until now, we are okay with it. Now, we're going to check to see what my coefficients and right-hand sides can do. How can they change without breaking the model? Now, what I'm talking about when I say breaking the model is just changing the optimal solution. Okay, how can optimal solution change? Now, in here, x1 and x2 is in the optimal solution, and they are the solution at one point. Let's just scroll down and you will see what I'm talking about. Now, this point B is my optimal solution. Now, as long as I am on this point B, wherever B might go, but as long as I'm on this point B, my optimal solution is the same. Okay, my values may change, my z value might change, my x1 and x2 values might change, but as long as I am on this point B and this point B exists, then my optimal solution is the same. It's the value of the model that changes. The value of the solution changes, not the solution itself. Okay, the optimal solution is going to be at point B. Now, how can I do the sensitivity analysis? We have to check a few different things. Let's start with, I don't know, the easiest constraint, the demand constraint. Now, as you can see, we have a feasible region from A to B to C and over here to the axis. Now, A, B, C, and here. This is the feasible region. This part isn't. This is an extra added shaded area. This isn't the feasible region. This is not in the feasible region. From A to B to C and over here. This is my feasible region. Now, in this shaded area, this area only, not the top side, in the shaded area, I know that B is my optimal solution because this here is my isoprofit line, and as it exits the shaded area, it touches B as the last point that it can touch. So B is my optimal solution, and I know that I have three different constraints here: the finishing constraint, the carpentry constraint, and the demand constraint. And I know that I have different right-hand side values for them. So, for example, for the demand constraint, let's go up. It says that it can be at most 40. X1 is less than 40. This is my demand constraint. This is the easiest constraint I can check because I can say that, okay, this is less than 40. I can increase 40 or I can decrease 40, and it will affect X1 only, just one value. Okay, let's try to do this then. If I change this value, okay, let's just assume that I'm changing this value, this 40. X1 is less than 40 is changing. If I increase this 40, it means that this line is being transferred to right-hand side, okay? As I increase 40, this line is going on, let's just say, going like this, okay? As I increase 40, this line goes like this to the right-hand side. And as this line goes to the right-hand side, values D and C will change. The points D and C will change. If this line goes to the right-hand side, this C point will be going over here, here, and it will end over here. If this constant, if this line is going to the right-hand side, the D point will be coming over here, and it will just merge with this one here. So if I merge 2 points, one of them just evaporates, let's say, okay? But this won't affect my point B at all because I can just keep increasing this demand constraint, and my point B will stay the same over here. It will not change, and B is my optimal solution, so I don't care about any other solution, okay? C and D are not my concern. B is my concern. So taking this demand constraint to the right-hand side doesn't change my B. I'm okay with it. What if I brought it to the left-hand side then? If I decreased my value. Now, if I start decreasing my demand constraint, my D point and my C point will be getting closer to B. As this line goes, for example, if it came here, let's not use arrow though, let's use something else. If it came just over here and increase the font, let's say, if it were here, for example. Now, in here, I can see that D point is over here and C point is over here. If I got closer, D and C will be coming closer to B. If I'm on top of B, which I'm not because I'm not good at drawing, but still, if I'm on top of B like this, then C and D will merge with B and B will, evaporate. So B will change, okay? The point B, my maximum, my optimal solution, B will change because of D and C getting on top of it. So I cannot take this demand constraint left anymore, okay? This is the most left I can take. So I can just get it over here to B, which is 20 points. Which means that if I can, let's just go back up here, let them see, it doesn't really matter. This 40 value can decrease to 20 and it can increase to infinity, okay? We have found limits for this value, okay? It can increase by 20 by infinity and it can decrease by 20. So this is part of a sensitivity analysis. This is an allowable increase and allowable decrease. Now, allowable increase and allowable decrease are going to give me the limits of a problem, of a model. Okay, how much of an increase can I have, how much of a decrease can I have for everything? For 40, it's 20 and infinity. Okay, let's go back. 20 and infinity. Cool. So this can decrease by 20 at most without breaking up my optimal solution, and increase for infinity. It doesn't matter because this constraint is non-binding and you can increase it as much as you want here because it's a maximization problem. It's above the shaded area, the feasible region, so it can increase for infinity. It doesn't change anything, but it cannot decrease more than 20 because it would break up B, which is my optimal solution. Okay, this is for the third one, which is not that hard to see. But what about the other two? What about this one, the finishing constraint, and this one, Carpentry Constant? Now, with these two, I have other stuff I need to check out. Now, I can increase or decrease them, yes, but by increasing and decreasing them, these two, which are binding constraints, by the way, I am moving B for sure. In this one, D and C were moving and coming over to B. But for example, if I increase the finishing constraint, let's go check the finishing constraint, this one, which is 100. 2x1 plus x2 is less than or equal to 100. If I increase or decrease this one, this value of B will change. For example, if I increase this 100, I don't know how many points, but just a few points, I'll be going like this. Okay, I'll be increasing this by increasing this constraint. I'll be sending this constraint up like this because the slope will be the same. The slope will not change because the slope is, let's just go up there and take a look. The slope is found from here, 2x1 plus x2. We are not changing these values, we are changing this value. So as the slope won't change, let's go down back, this will only move in this direction, okay, which is 90 degrees. So I'll be going up or down if I decrease this one. So when I'm going up with this line, if this concept goes up, what happens to B? Where does B go? Well, I'm going up, where does B go? Is it going up to A or down to D? Where does B go? If I
Down to D.
Down to D, right? If I increase this one, this, let's just annotate it as well, and we can see it easily. I will just keep drawing parallels to this line. So as you can see, it's coming over to D. So as it touches D, again, I will have broken my point. Okay, this B point will be merging with D now, and also C will be merging with D as well as you increase it. But still, this B will be moving and coming down to D. So this point will be my new optimal solution. Maybe, I don't know, we'll see. But still, this is the most I can get there. Okay, so what happens when I get there? How can I get there? So this D point is 40 to 40, right? So just go and write them, 40 and 40. Put 40 here and 40 here, so it will become 120. So I increase the right hand side by 20, which means that my increase for right hand side is at most 20. Okay? So this constraint can increase for 20 points. Now, we still haven't come to shadow price or reduce cost yet. We are talking about allowable increase and decrease right now. This is another part of sensitivity analysis, okay? We will get them soon enough. But in here, my increase is at most 20 for this constraint. What about my decrease then? How much can I decrease it without breaking my point B, without mixing my or getting rid of my optimal solution? Let's take a look. Oops, sorry. Annotate and clear. So if I start sending this constraint down, if it goes down like this, then B point, what will happen to B point? Where will B go?
Up to A.
Up to A. Again, you just need to draw some parallels, and you can see that it's going up to A, like this one. So as I decrease this value, it goes up to A. What about A? What happens at A? X1 is 80 and X2 is 0. And then all I have to do is just go there, put 80 and 0 over here, and see what happens. Oh, sorry. X1 is 0 and X2 is 80, the other way around. So if I put 0 here and 80 here, I'll get 80. So I have increased by 20 as well. All right, so the allowable increase and decrease for this first constraint are both 20. I can go up 20 or come down 20. It doesn't really matter. But these are my allowable increase and decrease values. So I'm done with the first constraint for allowable increase and decrease. what about my shadow price or reduced cost for the others? Let's start with the shadow price here because we don't really need reduced cost yet. Let's just clear it and take a look. How much of a value do I get by increasing this by 1 point? So when I increase this by 1 point, when this one goes to 101, what happens there? Okay, this line moves by 1 point. Okay, so if this one moves by 1 point, I will get to 101 over here, but here will be 50.0, 50.5. So it will be different. All I have to do is just find where this B point is. Where I have this point, where I have this B point done. So all I have to do is just solve where this B is. Okay, then I will find how much of a value increase I have gotten. Or I could just say, I don't know the solution. It's 20 to 60. So all I have to do is just use these values to get to 101. So I can just plug in 20 and 60 and see that, okay, this total is 100. It's binding, as I was expecting. So what happens when I get to 101? Now, these should just share that 1 point bonus like they have shared that 100 points bonus. So what happens there? Because I know that it's not breaking anything, it's not changing anything. All I have to do is just share it accordingly. So all I have to do is just use the Carpentry Constant, for example, and not solve the question. That's one part I can do. Or I can just share it between x1 and x2 in the ratio that they're already using. I can try that one as well. But still, you have to be very careful there because the best thing you can do is just find a new solution by intersecting these two, just by looking at this, graphical model. There are other ways, of course, you can do, but still, you have to be careful there. What about the other constant, the Carpentry Constant? Now, with the Carpentry Constant, which is over here, 80 to 80, again, I have the point B. If I increase this guy, so let's just take a look. If I increase this constraint, if I go with this one up, what happens to B? Where does B go? Let's just draw and see. If this goes up, I will get over here and then over here, I guess. Nope, a bit lower. Yes. So if this one goes up, as you can see, B is going up over here, up until here. So this is my new B, which also A is coming over here as well. So A and B are merging with this point. So this point is the most I can send it up. Okay, it's 80 to 100. 80 to 100. So it's actually 20 points of increase as well. So this constraint can increase by 20 as well. Okay, this allowable increase is 20 at most because B is coming over here and ending over here with the increase. What about the decrease part? If I go down, what happens? Let's just clear and take a look. If this one goes down, what happens there? Now, my B point, as the constant is going down as well. Let's just take a look. So from here, down here, and then from there, down to C, which is actually at point 40 to 20. Okay, 40 to 20. So let's just go and take a look what happens at 40 to 20. 40 to 20. 40 plus 20 is 60, which is a difference of 20 points. So this one is also, this second constant, the Carpentry Constant, can also go up 20 or down 20. Both the constants have the same increase or decrease allowance. It's all 20 over here. So this one can go, the third one, the basic one, can go down 20 or go up for infinity. All the other, just two of them, of course, but all the other constants can both go down 20 or go up 20 as well. So all the allowable increase and decrease are 20, except the increase of the demand constant, which is infinity. Up until here, we have seen all the increase and decrease. Okay, cool. But we have other stuff as well. We have to check the increase and decrease of these variables as well. Well, I only know that x1 and x2 are both in the solution. So they don't have a reduced cost. They both have a reduced cost of 0. And I don't need to check reduced cost of other variables. The S values, for example. I have 3 S variables, right? S1, S2, and S3. They don't need a reduced cost. Okay, why? Because I don't need them in the solution. Okay, being in the solution for any S values wouldn't be useful to me. Okay, I don't need, because S values are not something I'm producing and selling. They're just slack values. They are the amount of raw materials that are left for me. Okay, if they were in the model, For example, if it said that, okay, I can sell my, for example, this is finishing constant, my finishing hours I could rent out for this price, then S1 would be a decision variable as well. But it's not a decision variable now. It's just a variable, a slack variable that helps me, balance the model. Okay. The decision variables are just x1 and x2, and they are both in the optimal solution, so they have a reduced cost of 0. I'm not going to look for the reduced cost over here, but I will check it later on, of course, for other stuff, which you will see later on. But still, here I don't need to check the reduced cost for x1 and x2 because they have a reduced cost of 0. They are both basic variables. But I can check their increase and decrease, available increase and decrease. For example, okay, they are both in the model. They are both in the optimal solution. Why do I need to check their increase? Because an increase in x1 can mean that x1 can kick x2 out of the model, out of the optimal solution. And I said, okay, you just have to build me and sell me. You don't need x2 anymore. I'm so beefed up, I'm so pricey, I'm so expensive that you don't need to produce x2 anymore. This can happen. So a change in increase in x1 can lead to a kicking x2 out of the optimal solution. So I have to check, can it happen? When can it happen? It can happen, of course, but when can it happen? I have to check the value of increase over here or the decrease. If x1 is decreased so much, the price is decreased so much that it's not useful to sell anymore, it's not profitable to sell anymore, then x1 can leave the optimal solution and x2 can be the sole produced value, the sole produced product over here. So I have to check this one as well. And this is easy to check, not very hard. You will see what I'm talking about. This is checked by checking the slopes of your isoprofit and constraint lines. Okay. Now, in here, this is the isoprofit line. You can see here over here. So what I need to show you is how it moves. Let's just get to it. Now, this isoprofit line can go up like this. Remember this one? And I already know that if it exits at this point B, then B is my optimal solution, which happens over here. So this isoprofit line, which is the objective function, can increase like this, and it leaves the shade area, which is A to B to C to 40 over here, this area only. As you can remember, this is not part of the feasible region. This is just a wrongly shaded area in the book, but still, this B is the optimal solution, and this isoprofit line is where it touches the feasible region last. Now, this line, if one of the x values change, for example, let's go up, back up. This is 3x1 plus 2x2. This is the slope for 3x1 plus x2, which is minus 3 over 2. Now, as x1 value changes, for example, let's just draw a table over here, which will make it very easy to talk about, I hope. Now, we have x1, x2. Now, we have an original value of 3 and 2, right? And the slope is minus 3 over 2. Now, if I change the x1 value, for example, if I increase x1, okay, if I increase x1, the slope will decrease or increase in the negative sense, okay? So if I increase this up to 4, this will become minus 4, which means that this line will rotate. And as it rotates, this line will get higher on the x2 side and lower on the x1 side, okay? It will rotate like this. It will be starting to give x1 more importance. So its normal will be more and more parallel to x1, okay? This line will rotate. So if it rotates enough up to a point, it will fit on one of the constraints. Take a look at this line, okay? It can rotate two ways, on the clockwise or on the counterclockwise. If it rotates on the clockwise, which means that x1 is increasing in value, so x1 has a better value now. If it rotates clockwise, it will fit on this constraint, this finishing constraint, which is a slope of minus 2. So if I increase and fit on that slope, let's take a look. I will be having the same values like this constraint, which is 2x1 plus x2. Let's go back. And now, if I keep increasing x1 up to 4, I will just have, let's just write it, a slope of -2, which will be the same as the finishing constraint. Now, if I keep increasing the slope, I mean the value of x1, now this b value will change. This b value, it will not change, but will no longer be the optimal solution. Because if I keep rotating it more, c value will be more important. C value, the c point will become my optimal solution. Because now this slope, okay, this let's say optimal solutions, the objective function slope has to be between the slopes of its two binding constraints. Let me just, this is very confusing, I know, but take a look over here. Now, this is the slope for, not the slope, the normal for the, over here, as you can see, this objective function, okay? This is the normal for its objective function, it's the perpendicular value. Now, let's just, this is the normal, again, another one, for the this constraint, as you can see over here, the finishing constraint, and this is the normal, again, another normals, like this, for the carpentry constraint. Now, as you can see, this normal is between these two normals, okay? As long as this one stays between these two, you're optimal. Your optimal solution will not change. Your B point will be optimal. But if this normal leaves from here or from here, then your optimal solution will change, okay? This is the algebraic way to show it. So, as long as your red arrow is between your two blue arrows, you're okay. If it leaves them, you are changing your optimal solution. So, as long as my slope is between the slope values of these two constants, I'm okay. What about the second constant? One of them was -2. As you can see, this finishing constant was slope 2. And this carpentry constant is slope of -1. So, the x1 can go down. Okay, it can go down by 1 point to 2, which would make its slope -1. So for x1, I can increase it by 1 point to get to a slope of -2 and just fit on one of my active constraints, or I can take it down by 1 point and make it fit to the other active constraint, which would mean that I can just allow this x1 an increase of 1 point or a decrease of 1 point. So the allowable increase and decrease for x1 are 1 and 1. What about x2? I can do the same analysis here, the slope analysis over here as well. This point, these 2 points of x2 can increase by 1, which would give me 3 and 3, which would mean a slope of -1. Or it can decrease by 0.5, okay, which would make it 1.5, which would mean a slope of, again, -2. So the allowable increase for x2 is 1 point, the allowable decrease for x2 is 0.5, okay? So I know the allowable increase and decrease of x1 and x2, great. I also know the allowable increase and decrease of all the values in the, constraints, all the right-hand sides of the constraints, that's perfect as well. I also know that the, reduced costs are 0 because they are both basic variables, and I'm almost done with the sensitivity analysis. All I have to do is just now create a table showing all these things I have learned. Okay, now let's just create that table in here. Let's say I'll just use this one and create the table. It should be a long one, I guess. Now, what I will have here is allowable increase, like AI artificial intelligence, allowable decrease. Now I have x1, oops, a bit more left, I guess, and x2, and I also have the right hand side, okay, b1, b2, a bit more left, I guess, b2, and b3. The values for right hand side are called b. You will see later on why we are doing this, but still, x1 and x2 have allowable increase of 1 allowable decrease for x1, as you can remember. 3 can go to up to 4 or down to 2. Allowable increase for x2 is 1, allowable decrease is 0.5. Allowable increase and decrease for these 3 lines, they were the same, they were all 20, except for the allowable increase of the third constraint, which was infinity. So I can just write 20 all around, and say that the allowable increase for the third one, this demand constraint, was infinity. So this is my table, the sensitivity table. Okay, I can see everything here, the allowable increase and decrease over here. I also have the reduced cost, because I also know that the reduced costs were 0 and 0, and I can just find the shadow price and write them here as well. By the way, there are lots of easy ways of finding those shadow prices, which you will see later on as we talk about it. But still, from here, this is how we do it. From the graphical solution, this is how we do it. But there are other easier, let's say, solutions, because graphical solution only works for 2 dimensions. We need more and more, which we will see later on, as I said. But still, this is how we find the sensitivity part, how we find the values for the sensitivity. How can it increase, how much can it increase or decrease? Okay, what else? Let me just remove these. Of course, in this paper here, it just talks about everything, so you can see every calculations that we have done here in this PDF as well, which is in your as I said. But still, this one just goes on and on. Okay, what about the other parts? Now we have 100% rule, which we'll talk about after the break, and the Lindo example, which again we will talk about after the break. And they are about doing more complex sensitivity analysis, which you will see soon enough. So we will start with Lindo now. Max, you said, right? Max. What are we maximizing? Give me some numbers. Turkish or English doesn't matter, by the way. Give me some numbers. 3x1, 4x2, etc.
4x1, 7x2.
7x2. You can go minus or plus, it doesn't really matter. We can try anything right now. By the way, there is no wrong, model. We can try everything, and we can see if it's, infeasible or, unbounded. It doesn't really matter. Okay, being infeasible or being unbounded when you write here doesn't mean that you are writing a wrong model. And we can just tweak them to make them feasible or bound anyways. So what else? Let's make it bigger. For example, minus 3x3 plus 5x4. ST means subject to, which means that we are starting to write our constraints now. By the way, we can write however we wish, and we can just start over here or over here, but it needs to be the same syntax as the objective function. For x1, x2, x3, x4, it's expecting these values down here. So for example, 3x1 plus 4x3 plus 7x4 is less than or equal to 20, for example, stuff like that. So give me some constraints. You can write
artı x2 direkt olarak x1 artı x2 küçük eşit 30 desek mesela.
Okay. Now, your friend said less than or equal. I'm just gonna write less than, because in computer world, I don't need to write in this Lindo at this. I don't need to write equality over here. Less than is the same as less than or equal in here, because this is the difference is infinitely small. Okay, being equal or less than or equal. Yeah, I mean being less than or equal is infinitely small in this model, or in every model we will see over here. So we can write it just less than. Okay, it will just accept this as less than or equal and solve it like that. For example, it can give x2 the value of 30. Okay, it can just say x2 is equal to 30 and x1 is equal to 0. And every variable we write here, the same variable we write here will be considered non-negative. Okay, they will never have negative values. Okay, never. So what else? We need at least 2 more, I think. So give me some more.
Hocam x3 büyüktür 10 diyelim.
All right, what else? We have a greater than sign now. That's good. So this is not just simplex. We need big M or two-phase or something else as well. So what else?
Hocam bir tane de sign resurrection olsun.
We already have sign instructions. Those sign constraints are in here. It's embedded. It's accepted as like that. As I said earlier, they are all non-negative. They cannot be negative anyway. So sign restrictions are there always. So give me something more complex with all 4 of them together, if possible. Something like maybe, I don't know, 3x1 minus 2x2 plus 4x3 minus 2x4 is less than 10 maybe. No idea. Now,
Hocam eşittir işareti koyabiliriz değil mi?
koyabilirsin ama koymanıza gerek yok. Eşittir varmış gibi varsayıyor. Yani bunu
Tamam.
eşittir 10 olarak yapacak zaten veya bunu eşittir 20 olarak yapacak eğer bindingse.
Ha, anladım. Ben hani küçüktür yerine direkt eşittir koyabiliyor muyuz
Onu da yapabilirsin.
diye
Evet.
sordum.
Olur. Mesela x1 artı x2 eşittir 20 falan diyebilirsin.
Evet. Hı hı.
Böyle bir şansın var ama zaten şu varken bunu koyunca bu işlevsiz hale geliyor otomatik olarak. Şunu önce alacağı için belki başka bir şey olur. x3 artı desek falan şöyle gibi. Deneyelim bakalım ne olacak. Let's see what happens. Now we can just click solve and solve here. So it will just solve. So no feasible. It's infeasibility. It's an infeasible model. So we cannot find x values that satisfy all our constraints. Okay. So I have to check which constraints I have to make better, for example, to be able to solve this. And I would just say maybe increase this one greater than 40, let's say. If it happens, we'll see. No idea, I'm just trying. Still infeasible, so it doesn't work. Okay, let me just increase this one then and try like this. Still infeasible. Okay. Maybe this one. This is probably one of the reasons it's having problems. Let's try this one as well. Nope. Still infeasible. So this guy is causing us a lot of problems, I would say. Or maybe this one. Let's just try to give it more. Nope, still infeasible. Might be because of this one. Let's see. Yes, now we have an optimal solution. And now take a look over here. After we have removed this one, it says this is optimal. It can get there in 3 iterations, so in 3 steps. Okay, 3 simplex iterations, and the objective value is 342.143. Okay, and here we have the solution. Let's just increase this one as well. Okay, let's make it 36 as well. Now, again, step 3, so 3 iterations. And we have x1 is equal to 0, x2 is equal to 50, x3 is equal to 5, and x4 is equal to 1.42. These are my optimal solution values for all my decision variables, okay? This one is non-basic because it has a reduced cost. All these 3, x2, x3, and x4, all these 3 decision variables are basic variables because they have a value greater than 0, and they have a reduced cost of 0. So they are basic variables. If this reduced cost, this 5.14, was 0 as well, then this x1 would be a basic variable as well, but it would just be having a value of 0. Now, let's go back to the question for a second. Take a look at the question. We have 1, 2, 3, 4 constraints, which means we need 4 basic variables. But here, I only have 3 basic variables yet. I will see the S and E values downstairs, but still, I have 3 of them here, so at one of them, there's only 1 basic variable left, should be downstairs with the slack or excess variables. Let's go there. Yes, as you can see. The 5th row, which is actually the 4th constraint for our question, because the 1st row is the objective function, the 2nd row is the 1st constraint, and the 5th row is the 4th constraint. So, as you can see, this one has a slack or excess, depending on the question, but this should be slack, I think, yes, because it's less than or. And it has a huge slack, 122, which means that this one is actually in the minus. This part, this equation is equal to something in the minus values, because as we know, there's a minus 2x4 and there's minus 2x2, so x2 and x4 had values, I think, yeah, 50 and 1.42, minus 2 times 50, minus 2 times 142, so it's in the minus area. So this one is actually in the minus area, so the difference is something like 120, okay? So there's a huge difference there. It can happen, it doesn't really matter. So what else? Now, this is our basic variables, which means that these 3 constraints have a slack or excess that is non-basic variable, which means that they are fitting Okay, they are intersecting at one point, and that one point is our objective function's optimal solution. Now, these three are all active or binding constraint, and this is a non-binding constraint because, well, as you can see, it is a slack. And as you can see, the dual price for that one is 0. Why? Okay, why? Because the dual price, as you can, if you can remember that one, was the increase in your objective function value by, or the improvement in your objective function value by increasing your constraint right hand side value by 1. Yani biz, aşağı gönderdim pardon. Kısıtımızın sağ tarafını bir birim arttırdığımız zaman z değerimizdeki gelişme miktarına şey diyorduk, shadow price diyorduk. Bunu bir birim arttırırsam burası gelişmeyecek. Çünkü bunun zaten bir slack'i var. 120'lik bir slack var. Şurada eksi 80'lerde bu değer zaten. Bunu 41 yapsam da bu eksi 80'lerde kalacak. Bir şey fark etmeyecek. Çünkü bu binding değil. Kısıtlamıyor. Okay? This is not a binding constraint. So any increase to this right hand side value will not affect this left hand side. Okay? So there will be no change in your z value. So the dual price or the shadow price is 0. On the other hand, for these three, they are all binding constraints, so an increase in them might result in an improvement in your objective function. Note that this one is a minus. So if you increase the right-hand side of this constraint, you will get a lower z value. Okay, let's check if this is logical. And yes, it is, because this is a greater than sign. If I increase this to 6, I will be constricting, okay, or restraining the model more. Burada şunu söylemek istiyorum. Ben bu 5'i 6'ya çıkartırsam eğer, büyük işareti ya bu. Bu modeli daha da sıkıştırıyor. Çünkü 5'ten büyük olmakla 6'dan büyük olmayı karşılaştırırsanız eğer 5'ten büyük olmak daha geniş alan bırakır size. Ama 6'dan büyük olmak daha dar alan bırakır. Aynı şekilde 50'den büyük olmakla 51'den büyük olmayı karşılaştırın. 50'den küçük olmakla. 50'den küçük olmakla 51'den küçük olmayı karşılaştırdığımız zaman 51'den küçük olmak daha geniş alan bırakıyor. 50'den küçük olmak daha dar alan bırakıyor. Bu daha kısıtlayıcı. O yüzden daha kötü bir sonuç vermesini beklersiniz. 51 daha geniş, daha iyi bir sonuç verebilir dersiniz. 5 daha geniş, 5'ten büyük olmak, ama 6'dan büyük olmak daha kısıtlayıcı, daha kötü bir sonuç verebilir. Ki bu da onu söylüyor, daha kötü bir sonuç verebilir diyor. Eğer 6'dan büyük olmasını istersen eksi 5.85, yani birazcık daha değer kaybedersin diyor. So, if I increase the third constraint a bit, I will lose value in my objective function. So, for the first and second, any increase in them will result in an increase in the objective function value. Okay, these are my dual prices. That was the reduced cost, and now I have the allowable increase and decrease. How can my coefficients change? Now, these are the coefficients, the variables, coefficients of the variables. Now we have x1, x2, x3, and x4, and these are their values: 4, 7, minus 3, and 5. Let's check and see. 4, 7, minus 3, and 5. These are our starting values. And it says that you will keep this objective function, this objective solution, as long as your 4 does not go over 9.14. It has an increase range of 5.14, so 4 plus 5.14 is 9.14. And it can decrease infinitely. So there is no, limit there. So I can write this x1 should be minus infinity to 9.14287, whatever. So I can just write it like this. Let me just show you. Yeah, you can write x1 like this. X1, as long as x1 is in this bracket, so with minus infinity, because the allowable decrease is infinity, up to 9.142857, which is the sum of these two values. As long as x1 is between these two values, I'm optimal. Okay, I know that I'm optimal. There is nothing to look for. Again, with x2, as long as I'm between plus infinity and 1.86 something, I'm not sure. 7 minus 5.142857. It's a long one. So, but still, as long as it's between these two values, okay, between plus infinity, which is the upper limit, and 1.86, let's say, it doesn't really matter after the second one, but still 1.86. As long as I'm between these two values, I'm optimal. But this is just for one variable, just one of them changing solo. The others are not changed, just that one. Okay. For example, here, as long as I'm less than 2.857 and more than minus infinity, which is always almost, not almost, but always. So I'm good. There is no, break in the optimality. And here, the increase is infinity. I can go from 5 to infinity, but as long as I'm greater than 0, I'm okay, it says. So there is no change as well. So these are all my allowable increase and decreases that are giving me limits like this one. X1 can be between these two. All right. What about the others? These are just for the right-hand sides. What about the objective function? Sorry, these are just the objective function values. What about the right-hand side values? So it was 30 for the first one, and it says it can increase infinitely, but it cannot decrease more than 10. Okay, the second one was 50. Again, it can increase infinitely, but it cannot go lower than 0. Okay, this isn't that, let's say flashy, because in here, this is an increase of a decrease of 10 would get me to 20, and after 20 the optimality breaks. Okay, it changes. But with 50 I can go down to 0, and I cannot go lower than 0 because right hand side is always non-negative. So this is normal, but this isn't. Okay, it just limits me to 20. After 20 my optimality will change. Okay, and in here it can go to 0 again, but it cannot go above 7.5, or the optimal solution will change. Again, it can go infinitely up, but it can only go 122, and it actually allows me to get into the negative values. Okay, this one wasn't allowing me to get into negative values, neither was this one, but this one is allowing me to get to negative values because there are some negative, signs in there, as you can see. There were no negative signs here, so I cannot just go into the negative values with these ones. But in here, there are negative signs on the left-hand side, so I can go into negative values because this is probably something that is not a raw material. You cannot consume -2 raw materials or -2 raw materials like here. So it just allows me to go into minus values anyways. So this is just the basic Lindo stuff, all right? You can write as many, different solutions, different models you want to write here, and you can even use this to, check your work. Even in your exam, you can use this to check your work, but do not, try to copy your, let's say, solution from this, solution, because you will have to show the steps anyways. So try something like something different. Okay, someone is asking for the key in chat. So this one is Lindo, and let's just change a few things and make it more, I don't know, easy to relate, I guess. Make it all positives and see how it works like this. Okay. Now, this is more choose font, easier to check because these are all integer values now. Yes, so we have 140, just one of them, 20, x2 is equal to 20. All three of them have a reduced cost of, as you can see, 0, non-zero. So they're all non-basic variables. X2 is just one basic variable, so I have to see 3 basic variables down with the slack or surplus. So 1, 2, 3, yes, there are 3 basic variables. Now let's just change this a bit. I will add 2 to x4. So I'm trying to get x4 into the solution. Let's see what happens. Now this must be an alternate solution. This has to give me an alternate solution. Let's see if it can give me an alternate solution and how to understand the solution is alternative. Let's just go there and check. Now, again, I have the same solution. Again, I have x2 is equal to 20, x4 is equal to 4, but its reduced cost is 0. Now, this says that x4 is also a basic variable. It can be a basic variable. It doesn't have to be a basic variable right now, but it can be a basic variable if I want it to. Okay, it might be a basic variable in here as well. I have to check downstairs to see how many basic variables I have, but this says that you can be a basic variable, you can have a basic variable in x4. But it's a 0, so it's probably not a basic variable, but it's an alternative solution. There is an alternative solution here because a decision variable, which is x4 here, has a value of 0, but a reduced cost of 0 as well. It can be in the optimal solution. It allows it to be in the optimal solution, but I can see that there are 3, slack surplus values, so this is not in the solution right now. But if it was in the solution along with x2, we would see just 2 slack or surplus values with a plus, because that would be more than 4 basic variables. Okay, let's go back and change x3. It says that you can go up 11 points, so let's just send it up 11 points. Let's see what happens. 14. Is it gonna stay the same? I have no idea, by the way. We're just trying to see if something changes. We already know what's happening down there, but I think it will change. There's nothing changed. Again, it says that, okay, the solution we have found earlier is good enough for me. But as you can see, we have 2 zeros now in the reduced cost. Both x3 and x4 can be in the solution and give a value of 140. Okay, let's try to force them. I will try to force x3 and x4 into the solution. I don't know if it will break or it will be, let's just say greater than 1 and x4 is greater than 1. Let's try to force them. Now we will have 1, 2, 3, 4, 5, 6 basic variables if it works. Yes, sensitivity analysis, please. Now let's see what happens. We are trying to force them to be in the solution. And again, the objective function value will not change, 140. That's good. x2, x3, x4, all of them are in the solution now. That's nice as well. And we have 1, 2, 3 down here, so a total of 6 slack or surplus values. So I've actually added 2 new constraints, sending x3 and x4 to be, making them greater than 1. So they are both basic variables. They have to be basic variables. So x2 didn't leave the solution. If it did, it will be fine as well. This can leave the solution, letting x2, x3, and x4 just be in the solution by themselves, but still, it's in there. They all have a reduced cost of 0. They're all basic variables. No problems there. But as you can see, you can have alternative solutions giving the same value if the reduced cost is 0 and the value is 0 as well. Okay, so you can just force them to enter the solution and see a solution. And there are infinitely many solutions because it's an alternative solution. This is just one of the infinitely many solutions. Okay, there will be other solutions as well. We can see other solutions as well, giving the value 140. Let's try to force this one to be greater than 2, for example, instead of 1. Let's just do one more try. What happens then? As long as we don't break it, the invisibility part, we'll be fine. So I think we're okay there. The solution is again the optimal value is again 140. Same. And now it's 10, 4, 2. Oh, they are all integers. That's nice. They don't have to be all integers. We're just lucky here. 10, 4, and 2, again giving the value of 140. So it's okay. They are all different solutions to the same problem, the alternative solutions to the same problem. So this is how Lindo works, okay? We can see every sensitivity related stuff here. And one of the questions that I like asking, not in the first exam though, we won't see something that's in the first exam because it has to do with sensitivity. We will see in later on after the next week, hopefully. But one of my favorite type of questions is just giving you these values in terms of A, B, alpha, beta, etc., gamma, and telling you to find them. For example, I would just say, okay, this is alpha. How do you find it? Just try to find this value of 7. How can you find this value of 7? There are techniques which you will see later on, but they can also be, read from the optimal solution table. If you have an optimal solution table ready at hand, you can find these values as well. And there are other stuff we can do, which you will be, learning about them later on. As I said, it's not in the first exam, so you don't have to worry about this one for the first exam, the Lindo part. But knowing how Lindo works will be beneficial to you because you can just check if what you did is correct or not. Because in any given model, when you're doing the simplex, you might make mistakes. It's common. It happens. Even I make calculation mistakes. So I'm just the teacher. I'm just trying to teach. It doesn't make me superhuman. Everyone can make mistakes. So you can make mistakes as well, which means that you have to check your work. And this is the easiest way. Don't ask your friends. Just ask Lindo. It's allowed. Okay. During the exam, you can use this one because it's open book. And as long as you don't try to copy stuff from other websites or etc., other people, it's okay. But do not try to do anything more than what Lindo offers, of course, because it can just be considered cheating again. We will see. But still, this is pretty good because it allows you to check your work. Is the solution I have found correct? If you found something other than 140, for example, for this question, then you made a calculation mistake somewhere, and you can just go back and try to find it and correct it. If it's very close, you can just say, okay, I might get some more points. I'm just gonna go on to other questions. It's up to you because it's a time wasting effort. Trying to check your calculations, a time wasting effort in a way. The best way is, of course, to double check your work when you're calculating them, because that way you can make sure that you're not doing any mistakes, but still, it can happen. And here's a little trick for you. As you can see, this x1, x2, x3, and x4, these 4 constraints all start at value 0, right? So x2, x3, and x4 have to get one, let's say, one iteration each to get a value. For example, at the start, S1, S2, S3, S4, my select values, S6 or whatever, my all 6 select values in this question are, basic variables. At each iteration, one of them should leave, and then x2, x3, and x4, one of them should enter. So at 3 iterations, I should be complete. So which ones will exit? S1, S4, S6, or E6, whichever it is. I have to make sure that these 3 exits, from the optimal solution, these 3, and these 3 enter instead of them. So when we are finding the exiting and entering, variables in the simplex, we can consult here. Okay, for example, there is a situation where you can take, for example, S1 and S2, one of them should go out. They have the same, value in the objective function. So which one is going to go out? Lindo says the first one should. If I take the second one out, I will make more iterations to get it back later on. So Lindo says take the first one out. So I should take the first one out. You can use that stuff. That kind of intuition. It's okay. It's actually encouraged because that would make you creative, more creative, okay, when tackling stuff like this. But, don't try to use someone else's solution. It's not, well, let's say it's not ethical. That's it. So this is how Lindo works. What about other stuff? There are much more stuff as well. No, we don't need these right now. So one more thing to do over here. Let me just find, yes. Now, when we are talking about sensitivity, we have always talked about just one change, okay? Changing one part of the right-hand side values, just one of the right-hand side values, or one of the coefficients of objective functions. What if we change more than one at the same time? Now, this gets a bit more complex, and it's not that easy to tackle, but there's a very simplifying way of finding if we can still have optimality in a given situation, okay? And this is something very, let's say, easy to keep track of, but the negative side is you don't know if you have broken the objective function if this, rule doesn't hold. Now, the rule says that, it's called the 100% rule, and the rule says that, well, we have 2 cases. The first one is all variables whose objective function coefficients are changed, starting with the objective function coefficients, have non-zero reduced cost in the optimal row 0. Now, non-zero reduced cost means they are all of them, all the coefficients we have picked come from non-basic variables because they have a reduced cost greater than 0, okay? They have non-zero reduced cost, so they are non-basic variables. Or at least one variable whose objective function coefficient is changed has a reduced cost of 0, so it is a basic variable. Or part of the, alternative solution. Yeah, couldn't remember that one. So it's either a basic variable or part of the alternative solution can be a basic variable at a moment's notice. So it's either all of them are non-basic or at least one of them is basic or can be part of the optimal solution. Now, as an alternative solution. Now, in the first case where all of them are non-basic variables, as long as they stay in their ranges, the solution is still optimal. You don't need to do anything in there, okay? As long as all of the non-basic variables stay in their ranges, they can change at the same time in any way they want, and the optimal solution will still be the same, okay? It won't change. But all of the non-basic variables should be in their ranges, okay? But in the second case, if at least one of them is a basic variable or part of the alternative solution, which has a reduced cost of 0, then we have to check their allowable increase and decrease values. Now, this will come, actually, using Lindo here would be very nice as well, so I will get back to it. But the thing is, when you have, let me just write this. And let's have 3 of them, and then subject to, I'm just gonna create some simple model so you can just use it to.
We can see the window in our section, right?
I will share window after I've created the model, don't worry. For X3 is, I'm just trying to write it fast and then share it later on and see if it works. It's optimal, yes, give me, let's see, yes, nice. Okay, this one works.
Hocam Windows'a geçmeden case'leri bir kez daha açıklar mısınız?
Tamam. İki case var. Birinci case'te bütün şeyler, seçtiğimiz katsayılar amaç fonksiyonunda, yani şeydeki amaç fonksiyonunda seçtiğimiz katsayılar değişkenlerinin reduce cost'unun non-zero olduğu durumda. Yani bütün değişkenler temel dışı değişkense diyor. Yani temelde değil, yani şeyde değil, çözümde değil bunlar diyor. Çözümde olmayan temel dışı değişkenleri seçtiğin zaman hepsinde diyor. Bunlar şeyde olduğu sürece, kendi kısıtlıklarında olduğu sürece, allowable increase ve decrease'inde olduğu sürece sıkıntı yoktur diyor. Allowable increase ve decrease'nin içinde kalıyorsa eğer bu arkadaşlar şeyi değiştirmezler diyor. Çözümü değiştirmezler diyor. Şimdi bir saniye şeyi de bir aslında bir değiştireyim. Şuraya bir tane export diyelim. Bir taraftan da bir şey eklemeye çalışıyorum. Yeni bir değişken eklemeye çalışıyorum ki onun da şey olmadığını görelim. Bunu kapatıp öyle yapmam lazım tabii ki. Okey, şimdi oldu. Güzel. Şimdi ikinci case'te ise diyor ki en az bir tanesi, bu seçtiğin değişkenler en az bir tanesi ya temel değişken olsun ya da alternatif solution verebilecek bir şey olsun. Yani şey içerisinde olmasın diyor. Söyleyin adını. Reduce cost'u non-zero olsun diyor. Sıfırdan büyük olsun diyor. Ha. En az bir tanesi şey verecek yani diyor. Pardon, reduce cost'u zero olsun diyor. Sıfır olsun diyor. En az bir tanesi temel değişken olsun veya alternatif çözüm olarak temel değişken olarak yaratabilecek bir şey olsun diyor. Now, let me just give you the new share and show it on window. Now, let's take a look over here. Now, in here we have a simple model with 4 variables. Let's choose a new font. Increase the model as well. 4 variables, 3 constraints, so we can have at most 3 basic variables, and this is the solution. Now, as you can see, we have 2 basic variables from our decision variables, x1 and x3 as basic variables, and 2 of them are non-basic, which is something I was going for. So this is nice. 2 of them are basic, 2 of them are non-basic. So for case 1, all variables whose objective function coefficients are changed have non-zero reduced cost. So I can change x2 and x4 at the same time. Let's go down. x2 and x4 over here. x2 was 2, x1 was 1. So I can increase this at most 0.75 point. I can increase this at most 2.25 points. So if this 2 becomes 4 and this becomes 1, this 1 becomes 1.5, the optimality won't change because this one is allowed to go up to 4.25 and this one is allowed to go up to 1.75. So if this 1 becomes 1.5 and if this 2 becomes 4, they are still in their range, okay? So they haven't changed. They are allowed to be there, so the optimal solution will not change, okay? This is certainly. But if at least one of them breaks its optimality point, the limit, so it will just upset the model and optimality will change. We will lose our optimal solution and try to find a new one. Finding new optimal solution is a whole new, subject. We will see them after the exam, hopefully. So the second one, at least one of them is inside the solution. So at least one of them has a value of 0 in its reduced cost part. So either x1 or x2, or maybe take both of them. Let's just take both of them to make it easier. Now, I have a reduced cost of 0 and a reduced cost of 0. I will just change these two, okay, x1 and x3. Let's go down. x1 has a value of 1, x3 has a value of 3. Now, as you can see, they are both allowed to go infinitely up. So if I change them up, it doesn't really affect me. Because the 100% rule says that when you make a change, note the amount of change in percentage. So this is an infinitely many. You can go up infinitely many. So if I change this 1 to 5, it's 4 over infinity, which is 0%. If I change this to 10, it's 7 over infinity, so it's 0 as well. But I can go down with them. So let's try. So if I take this one, let's just annotate them, and take this one down to, let's say, 0.5. Now, if I take this one down to 0.5. Then the amount of change I'm making is 1 minus 0.5, again 0.5. So in percentage wise, it's 0.5 over 0.75. So 1 over 2 over 3 over 4, which is, I don't know, what, 1 over 2 over 3?
6%.
2 over 3? What? 2 over 3, right? 66%. Right?
Yes.
All right, 66%. So the amount of change is 66%. By the way, it doesn't matter if it's going up or down. Okay, this is the absolute value. This is minus 0.5 normally, but it's the absolute value of it. Okay, the change is 66%. What about here? If I took this one down, again 0.5. Let's say it goes down 0.5. So I'm looking for 0.5 over 3. Now this is 1 over 6, 16%, 16.6%, I guess. So my total change is 66.16, 18.2.3, doesn't really matter, but still the let's just write it by rounding it up. 83%. The total change is 83%. All right. Now this 83% is less than 100%. So the solution is still optimal. Okay. As long as this change in percentage, the sum of all the changes and absolute values of them is less than 100%, the solution is still optimal. We can say that, okay, this solution is still optimal. This is accepted as this one. But if the percentage is above 100%, for example, let's say that the last change isn't 0.5, but let's assume that it's 2. So I'm taking it down to 1 from 3 to 1, going from 3 to 1, which is going to be a change of 2 points out of 3. This is allowable decreases 3. So my change is again 66%. Now I have a total of 133, right? Percent. Now, in this one, we cannot say anything. This still might be optimal or suboptimal. The optimality might have been, lost. This is, well, it's just not clear. We cannot be certain. Okay, there might be things we can do, to be able to show that this happens. This may not break optimality. For example, think about it. If I said that, okay, I'm gonna just change the coefficients like this: 2, 4, 6, and 2. Okay, I've increased this one by 1 point, by 2, by 3, by 1 point again. Is the optimality gone? Are we still optimal or not? Is the solution still optimal or not? Can you say anything? Any idea? Is the solution still optimal or not?
Not optimal.
Not optimal. Why not?
Because the X4 exceed the limits, 0.75 limit.
Okay, X4 was not in the solution, right?
Yes.
Okay, but this is wrong. This is still optimal, by the way. Why? Because all I did was just multiply everything by 2. Remember, multiplying a line by something doesn't change the solution. It's whether it's a constraint or the objective function. I just multiplied everything by 2. Everything has increased a lot. So they are out of their bounds, yes. But everything has been multiplied by 2, so everything has changed. It's not just the, it's not just the basic, non-basic variables. It's both basic and non-basic variables, okay? The first case says that if it's all non-basic variables, then they all have to stay in their, limits. But here, we are changing both basic and non-basic variables, so we have to check the 100% rule. But the 100% rule will not give us anything because it's going to be above 100% anyway. But this is just the multiplication of the objective function by 2, so it's still optimal. It has still the same solution. Just the objective value will be greater, double it. That's it. But still, it's the same. There are some tricks you can make like this to make life easier for you to see if it's changed or not. But still, you can just say that as it's the double, everything is double, from before. So the solution is the same, but the value has changed. Okay, optimal value. The optimal solution is the same solution with the same x values, but the value has doubled. That's it. So there are some tips and tricks you have to, see and understand how this works. Any questions with this one? All right.